Well, we have seen about the Gauss-Markov model and the Gauss-Markov theorem. I also mentioned that it was the theorem that we have seen so far is just a simple version of the Gauss-Markov theorem. Let's quickly recall what that was. In that theorem, we have this thing. We have the Gauss-Markov setup. We assume that x prime x is a non-singular matrix, and then we took any C and we said that C prime beta hat happens to be blue, the blue of C prime beta. I also mentioned that this non-singularity of x transpose x, which by the way is equivalent to all the columns of x being independent, that is x being full column rank, that condition may be dropped. So the general version of Gauss-Markov model is going to be something like this. We will still work with the Gauss-Markov setup, but we shall not assume that x prime x is non-singular. As a result, we have to sacrifice something. We now cannot work with any C. We need some condition on C under which the same conclusion will work. Now let's try to understand what that extra condition is going to be. The condition is already given in the book, but let's try to understand intuitively what that condition should be. So let's take this example. In this example, I have given you a simple linear model. So the first line is y1 is beta 1 plus beta 2 plus beta 3 plus epsilon 1. The second one is also same, except that the error has changed, and in this way you have the first 5 lines all having beta 1 plus beta 2 plus beta 3. So we are measuring something which is beta 1 plus beta 2 plus beta 3 and with some errors. The remaining lines from line 6 to line 9, 4 lines, all have beta 1 plus beta 2 plus twice beta 3. Okay? And I assume Gauss-Markov setup, epsilon i's are all mean zero, uncorrelated, homoscedastic, etc. Now I ask you this question: how are you going to estimate beta 1 and beta 3? Just think in common sense way, no least square or anything, and you can guess very easily, sort of feel very easily, that beta 1 you cannot estimate from this setup. Why? Because beta 1 is always bundled with beta 2. Wherever beta 1 occurs, it occurs as beta 1 plus beta 2. So you do not have any hope of extricating beta 1 separately. So if you are trying to get beta 1, beta 2 will always be there. But beta 3, there is hope to get hold of that, and that is pretty simple. What you do is this: you take, say, the first row, and you take this sixth row, you subtract the sixth row from the first row, and you can get hold of beta 3. So if I take, say, y6 minus y1, that will be an unbiased estimator of beta 3. I am not saying it is the best estimator, but it's a meaningful thing. You can do that. But beta 1 you can't do. Now, if I want to make this precise, here is one way of making it precise. I might say that it is possible to get 2 sets of beta i's, that is beta 1, beta 2, beta 3, 3 values, and 2 sets of such values, for each of which beta 1 plus beta 2 plus beta 3, that is this combination, and beta 1 plus beta 2 plus 2 beta 3 will be the same. Yet, beta 1s are actually different. So it is possible to get that. Because it is possible to get that, so you cannot say I can find beta 1 uniquely. You understand, it is like this. I give you 2 numbers. Say. I have one number A in my left hand and another number B in my right hand. I add them up. I get the answer to be 10, and I ask you to find out A and B individually based on that information. You can't do that. If you cannot do that, even when I give you A and B, A plus B exactly, you have no way of getting A and B if I give you A plus B only approximately. So that is the idea. In this case, if I give you beta 1 plus beta 2 plus beta 3 exactly, no epsilon, So all these y1 to y5 are same, and that is exactly beta 1 plus beta 2 plus beta 3. Similarly, I give you exactly beta 1 plus beta 2 plus twice beta 3. Even then, you have no hope of obtaining beta 1, right? So if you cannot obtain beta 1 even from the precise data, precise information, how on earth can you hope to get it when you have errors epsilon 1 to epsilon 9? You understand the point? So we generally say, that's the term, that beta 1 is not identifiable from this setup. Meaning that you can have multiple values of beta 1 with possible adjustment in the other parameters, which will give rise to the same data. So I can have beta 1 equal to 1 and beta 2 equal to 5, but I could have beta 1 equal to say 2 and adjust beta 2, make it 4. So beta 1 plus beta 2 still remains 6. You cannot say whether 1 comma 5 was the situation or 2 comma 4. Now if I want to express it as a condition, here we understood it intuitively. If I want to understand it as a rigorous mathematical condition, let's look at it in the following way. I had my, what should I call it, the design matrix. So this is my design matrix. And what is my beta 1 after all? Beta 1 and beta 2 are nothing but two linear combinations of beta i's. For beta 1, the linear combination is beta 1 is 1, 0, 0 times this, and beta 3 is 0, 0, 1. Now the point why we could not obtain beta 1 separately was because I could not express beta 1 as a combination of these equations. For example, for beta 3 I could do that. I said I will take this equation, subtract the top equation from the sixth equation, I will get beta 3, which basically means I take this row of x, from it I will subtract that row, and I will end up with 0, 0, 1. In this case, I cannot do that. So it should not come as a great surprise that the condition of identifiability in this case reduces to checking whether this vector belongs to the row space of X. The condition of identifiability, the very concept of identifiability, is nothing very special to linear models. It is true for any statistical models, but in this special case of linear model, it turns out to be the following linear algebraic condition: C prime beta, this linear parametric function of beta, is identifiable if and only if that C belongs to the row space of X. So that is the condition of identifiability. If C does not belong to the row space of X, it is just a meaningless problem to try to estimate it. Howsoever technique you try to use, it's just a meaningless problem, something like estimating beta 1 when beta 1 is always present as beta 1 plus beta 2. On the other hand, we also saw that if C belongs to the row space of X, then you can get some way of estimating it just by taking appropriate linear combinations of those rows of X using which you can express C. So we immediately get another consequence that we have already discussed. It says that if that is the case, in that case there exists some linear combination of the data whose expectation will be that C prime beta. We have already seen that, but just let us remind ourselves how we got that. We did it in this way. Suppose I take this simple case, y1 is beta 1 plus epsilon 1 and y2 is beta 1 plus beta 2 epsilon 2. And my job is, say, to estimate beta 2, which means I am working with C prime beta, which is beta 2, that is C is here 0, 1. Now how do you go about doing that? You can immediately see that I can take the second equation, from it I will subtract the first equation, beta 1 will get cancelled, so I will get y2 minus y1, and that will be an unbiased estimator of beta 2, because epsilon 2 minus epsilon 1 will have mean 0. Both the epsilons have got mean 0. Linear algebraically, what I may say is this thing. So this thing is that 0, 1, that is my C here when I am trying to estimate beta 2, and this is my design matrix 0, 1, 1, 1. So I expressed these as a linear combination of the rows, namely this I multiplied with 1 and this I multiplied with -1, I added, subtracted the first row from the second row. I play the same trick on y. Take y2 from it, subtract y1, and that will give you an unbiased estimator of beta 2. That is precisely what I am saying. You can find a v. In my case, the v will be +1 here and -1 here, 1 minus 1, such that take the linear combination of y with those coefficients, expectation of that will be c prime beta. So that's a very good news. Whenever you have something which is identifiable, linear parametric function which is identifiable, you know it is a meaningful thing to try to estimate this, but immediately you also get at least one way by which you can actually estimate it using a linear function of the data. And that estimator will also be unbiased. Not necessarily the best or anything, but at least you have one way of doing it. So we call such a thing linearly unbiasedly estimable. So identifiable turns out to be synonymous with linearly unbiasedly estimable for linear models. I said synonymous, so though I have put this one implication, it is rather trivial to check that the reverse implication also holds. So if it is identifiable, then immediately you have a way of estimating it linearly and unbiasedly. Now, this linearly unbiasedly estimable concept occurs so very frequently in the world of linear models that we tend to drop these two adjectives, linearly and unbiasedly. And these are not really adjectives, these are adverbs. So we just drop them, we just call them estimable. So whenever you hear the term estimable in a linear model context, you understand we are talking about linearly unbiasedly estimable, and that is equivalent to this being identifiable. So if it is meaningful to estimate it, you can estimate it linearly and unbiasedly. So now let's get back to our Gauss-Markov theorem. We had seen already that we are trying to make it more general. We said that we are going to remove that condition of that x transpose x being non-singular. We do not want that. We want to work with any general x. And you have also guessed that we cannot anymore work with just any c. We need to put some further restriction on c. Now, that immediately implies that what kind of restriction should we put on c, and we discussed that, and we found that one restriction that is kind of the very basic minimal restriction that we should put is that we must have c belonging to row space of x, because if that is not the case, it is not even a meaningful problem to try to estimate c beta. Nobody can meaningfully estimate c beta, let alone obtain blue or whatever. So that is the basic minimal condition. Interestingly, that is all that we need. So that minimal condition is enough for us. We can then say precisely the same theorem, c prime beta hat will be the unique blue of c prime beta. So that is the general form of Gauss-Markov theorem. Now, how to prove this? The proof is pretty straightforward and follows essentially the same argument what we used for proving that special case, with one catch, and that is a serious catch. You might expect, suppose I try to show that it is unbiased, just do that. Well, how will you do that? You apply expectation on that, and you expect c being a constant thing, expectation will go through it, so c will come out of expectation and it will work with expectation of beta hat, right? No, that won't work. Simply because once I have dropped the condition that x prime x is non-singular, beta hat ceases to be uniquely defined. There are infinitely many possible beta hats, all of them least square estimator. Which one of them are you talking about? So you cannot say, I will take expectation of that. That's where we have to use a little linear algebraic trick, but after that everything will follow through, and exactly the same proof as in the simple case. Once we have settled this issue, what is exactly meant by c beta hat when beta hat is not even uniquely defined? For that, let's focus our attention on this condition c belonging to row space of x. You understand that row space of x is same as column space of x transpose x. No problem with that, because row space of X is column space of X, which contains anyway column space of X transpose X. Their dimensions being same, they are actually the same. So C actually belongs to column space of X transpose X. What does that mean? If something belongs to column space of X transpose X, you can immediately say that C may be expressed as that matrix X transpose X times some vector. No problem with that, because the columns of X, you take a linear combination of the columns of X and all the coefficients you put here in D. So C is X transpose X into T. So now let us see what happens when I work with C transpose beta hat. So that is the quantity, this C transpose beta hat. That is the fellow which we have to work with. We know beta hat is not unique. You take any beta hat, any least square estimated beta hat, C transpose this, then this becomes C transpose is D transpose X transpose X. Remember, this is a symmetric matrix. So taking transpose has no effect on that, times beta hat. Now notice that beta hat, whatever it is a solution of the normal equations. What was the normal equation? X transpose X beta hat equals X transpose Y. So whatever beta hat you take, X transpose X beta hat must be equal to X transpose Y. So you see, it is here that the non-uniqueness of beta hat nicely goes away. So now you obtain something which is completely free of beta hat. No non-uniqueness plagues this expression. It is just D prime X transpose Y. Find quantity. This is a fixed known vector. X is a known matrix, fixed. Remember, D is completely known because C you are given, that is what you are trying to estimate, C prime beta, X you are given. So you can express this and obtain that. D may not be unique, but you just take any one such D, that is enough. It will always give you the same C. And now, so it is a completely known fixed vector, and Y is the random thing. So you can find expectation, etc. using this expression. So instead of, when you apply expectation, taking C out and applying the expectation on beta hat, you take this D prime X prime out and apply the expectation on Y. So once you do this little trick, now the rest of the proof of the Gauss-Markov theorem remains just unaltered. So I will leave that as an exercise, and anyway, if you have problem, you can always look up our textbook. Now in our textbook, there is a little kind of weird thing. The textbook assumes that we are working with X prime X non-singular, yet the textbook uses this proof. So if you are really assuming that X transpose X is a non-singular matrix, then you really do not need to go through all these things. You do not even need to define what is meant by estimable, because then everything will be estimable. That's why in the simple version I could work with any C. So the book actually works with X prime X being non-singular but provides this general proof. So that is kind of weird, but this is the general form. So you have learned one of the most important theorems of linear models, namely the Gauss-Markov theorem. It's very pleasing in the sense that we put just the barest possible restriction on the parameter that we want to estimate, the linear parametric function that we wanted to estimate, and we got in a very constructive way the best linear unbiased estimate. So you might think that we have reached the holy grail of linear models, but no, there are problems. In order to arrive at that nice result, we have put a number of assumptions. If those assumptions are violated or nearly violated, then this optimality will be of no use for us, and in real life that is often the case. Take for example the situation, I take for example the assumption that all the sigma square have the same variance, they are all homoscedastic. In many practical situations we will find that they are either correlated or they are not homoscedastic. As I said, when I am measuring the length of something, if I make some of the measurements using a very precise instrument and some using less precise instrument, in that case you will not naturally be comfortable with taking the simple average. So if the errors violate this assumption, or we have this situation that is not equal, then we need to generalize this concept, which is called generalized least squares. We will go into that later. So this is just to remind you that the Gauss-Markov theorem is not something like you just put everything blindly into it and whatever comes out of it, you believe it blindly. Now here is another way by which things can go wrong. I am assuming that I am working with a situation where there are no outliers. Now every statistical method, when it is originally created, assumes that there are no bad observations. In practice, there may be some outliers. That is quite possible. Now, the least square estimators that we get generally are not robust. For example, even in case of measuring just a length, the least square estimator was the mean. And we know that mean is not robust. So if there are one or two outliers, some measurements that are quite far away from the rest of the measurements, those far away measurements will pull the mean towards it and completely ruin it. So if you suspect that there will be outliers, then you should use robust techniques, and robust estimators in general are not linear. So the fact that something is blue is not going to help you, because it is the best among unbiased linear estimators. It is not that it is best and linear and unbiased. It is best among unbiased linear things. So if there are nonlinear things, they might be better. So no one said that you should always focus your attention on linear things. Especially when you have outliers, nonlinear things might far outperform the linear estimators. A similar point is about unbiasedness. There are situations, in fact, very commonly occurring situations, where you have what is called multicollinearity. Now, multicollinearity means that the columns of X have got some approximate dependence. Something like this: suppose you measure height of a person in inches, and very stupidly also measure height of the same persons in centimeters. So because of some amount of numerical error, measurement error, these two things will not be exact multiple of each other, but very nearly 2.54 times one will be the other. So because it is very nearly, so they are independent but almost dependent. In that case, you will find that X transpose X is nearly singular. You understand, right? Because if those two columns are exact multiples of each other, then the rank of X will be one less. Here it is not one less, but on the verge of being that. In such a case, you will find that allowing a little bit of bias is a much better idea than working with unbiased estimators. Unbiased estimators, like least square estimators, will have tremendously high variance. If you allow a little bit of bias, you can reduce the variance a lot. So the total bias variance thing will be better. What is called the mean squared error will be better. We shall see one such example later, the ridge regression. The point here is that do not blindly trust the Gauss-Markov theorem. It is correct, it's a mathematically proven theorem, but the assumptions that go inside them may be violated. In that case, the conclusion is also a great suspect.